afternoon, everybody. I am Natalia Ruiz, the program manager of the Pire Create project. Welcome and thank you for joining this climate change webinar series. Today we have Professor and Pire Director Mathias Vuille and Thomas Favata, graduate student, talking about climate change and extreme events over the Americas. If you have questions during the presentation, please write them up at the chat. We will answer them at the end of the talks. And without further delay, let's begin with the webinar with Professor Vuille.
Thank you, Natalia. Welcome everyone for joining us here in this webinar series. So today I, together with Thomas Favata, will talk a little bit about climate change and extreme events over the Americas. I would also like to encourage you to visit our website at pirecreate.com and learn a little bit more about our project. We're a group of scientists from the United States, from Brazil and Argentina, who work on understanding how climate has varied in the past and how it will continue to change in the future. And we do that with the goal to actually inform policy and decision makers about the risks of climate change. For us, it's also really important to engage students in that work, both graduate students and undergraduate students. We have all kinds of activities, which unfortunately this year with the pandemic, we had to scale back, but we hope to certainly be back next year. Visit different SUNY campuses to engage undergraduate students. We also offer opportunities abroad, such as internships, week-long trips abroad, such as in Peru that are planned for next year, where some of you could potentially participate. Okay, so I want to give you a little bit of an overview about climate change, why it matters, what we know, and what some of the impacts are, but also what we can actually do to address some of these climate change issues. And oftentimes climate change is framed sort of under the umbrella of temperature change. We often talk about global warming. And what you see here in this figure is what we sometimes refer to as the fever curve of our planet. It shows how temperature has increased over the last roughly 140 years. These different colored lines, these are estimates from different research centers around the globe, but they basically all show the same thing. They show how that our temperature has increased by about 2 degrees Fahrenheit over this time period. The other thing I wanted to point out is that when we do climate science, we usually don't look at absolute temperatures, but we almost always use anomalies or departures from a long time mean. So you can see that the numbers here, they look fairly small, and that's because they are actually anomalies compared to this baseline reference period. So whenever you have number of years above this gray line, it means the temperature was by this amount warmer compared to this 30-year period from 1951 to 1980. Now, why is temperature going up and down? There's a number of reasons for that, and sort of the natural reasons for why this occurs we'll talk about next week. But the overall increase over this 140-year period is driven by an increase in greenhouse gases in our atmosphere. And the most important one of these gases is carbon dioxide, CO2. And I think it's important to get a little bit of a historical perspective as to how we actually know this and how we have learned about this climate change science. Because sometimes there's this misconception that this is something very new that scientists are still trying to figure out, and we don't really understand the processes. But that's really not the case. We've actually known about the basic science behind the greenhouse effect for a long time. And this started almost 200 years ago with work by a French scientist, Vuille, who was the first to really realize that there must be constituents in our atmosphere that keep our planet warm. He tried to calculate the energy balance of our planet, and he realized that based on his calculations, our planet should be much, much colder. Actually, there should be no liquid water on our planet. Everything should be frozen over. And the only reason that is not the case is because of these greenhouse gases that keep our planet warm. So it's also important to recognize that greenhouse gases, they're not fundamentally bad. In fact, they are absolutely vital to our survival. We need these greenhouse gases in our atmosphere. It's just then when the concentration becomes too high, it becomes a problem. So Joseph Vuille already realized that, but he didn't really have the lab, the equipment to prove that he was right. And it took another 30 years or so until John Tidal was able to measure in the lab that if you expose CO2 to infrared radiation, that much less of that radiation will make it through the air mass, meaning that CO2 absorbs the infrared radiation and radiates it back in all directions. And then still another 30 years later, a Swedish scientist, Svante Arrhenius, was the first to actually pose the question, well, what would happen if we double the CO2 concentration in our atmosphere? And he came up with a number of roughly 5 to 6 degrees Celsius of warming. Turns out that number is too high. We think it's more on the order of about 3 to 4 degrees Celsius. But it's also important to realize that all of these scientists in the 19th century, they were not concerned about climate change the way we are. This all happened at the start of the Industrial Revolution. They were more interested in understanding the energy budget of our planet. And it was only in the middle of the 20th century when Roger Revelle and Hans Suess were the first to pose the question about what we're actually doing to our planet, and that we're carrying out an experiment with unknown outcome. And by that point, we knew we were already emitting large amounts of CO2 into our atmosphere, but we didn't know where the CO2 was going. Maybe plants would take it all up. Maybe it would all end up in the ocean, a big carbon sink. We didn't know because we couldn't measure the amount of CO2 in our atmosphere. And it was that same year that Charles Keeling built a device and deployed it on Mauna Loa in Hawaii that could actually measure the CO2 concentration in our atmosphere. And that turned out to be a groundbreaking discovery because that led to this, what is now known as the Keeling curve, these measurements of CO2 in our atmosphere. And that's what you see here on this figure. And we measure CO2 in parts per million. And you can see that since these measurements started, the actual concentration has increased by more than 100 parts per million. We're now at about 415 parts per million. And this is a really, really important discovery. If you ever have the chance to visit the National Academy of Science in Washington, there is a wall in that building, and engraved in that wall are some of the biggest scientific discoveries of our lifetime. And you may recognize some of them. They're the Darwin finches that highlight the discovery of evolution. You see the DNA double helix, the groundbreaking discovery in microbiology. And you can see here in the upper left corner, the Keeling curve, arguably the biggest discovery in geophysics in the 20th century. The fact that we as humans are rapidly changing the chemical composition of our atmosphere. Now, if you're a critical student, you should say, well, okay, that's fine, but these are very short measurements. They only started in the 1950s. Maybe a few thousand years ago, the concentration was much higher than it is today. And so even though we only have this short time period of actual measurements, we have a very good sense of what the CO2 concentration in our atmosphere was going back 800,000 years. And that's shown in this figure here by this red line. Because we can actually take measurements from Antarctica by drilling into the ice, extracting ice cores and bringing these cores back to the lab, we can see in the ice tiny bubbles of ancient air that is trapped in the ice. And we can take measurements of the CO2 concentrations in these tiny bubbles. And that gives us, shown here by this red line, an estimate of how CO2 has varied for the past 800,000 years. And if you look closely, you can see that this line goes up and down and up and down, and it takes about 100,000 years for this line to go up and come back down. And that's exactly the length it takes for one ice age to come and go. So what you're seeing here by these 8 peaks and these 8 troughs are the last 8 ice ages. The last time an ice age peaked was here about 21,000 years ago. Albany was under a massive ice sheet. And every time we hit an ice age, here, the CO2 concentration dropped. Every time an ice sheet ended and it became warm, we call these so-called interglacials, the CO2 concentration went up. But you can also see that the CO2 concentration never went above this blue dashed line, which is at about 300 parts per million. By the end of the century, we will be somewhere here in this range, depending on how we continue to burn fossil fuels, somewhere between maybe 550 and almost 900 parts per million. Right now we're here at 415, and we're going up this ladder by about 3 parts per million every year. And this is really not a scientific question, what we're doing here. This is not a model, this is actual based on observations. It's really just more of a ethical or a societal moral question as to what world we want to leave behind for future generations. So why are we emitting so much CO2, and why is nobody doing anything about it? I think it has a lot to do with the fact that CO2, it's kind of a funny gas in the sense that we're all emitting it, but we can't see it. We can't smell it, we can't hear it, we can't feel it. So we're oftentimes not aware of how much CO2 we actually emit. So a few years ago, some scientists teamed up with artists to try to visualize how much CO2 we emit. And I want to show you a quick video that highlights how much CO2, how much the city of New York alone emits. So we're going to go forward here a little bit. Okay, I will stop this here, go back to the presentation. So I think you've gotten a sense of what is actually happening here. We're basically using our atmosphere as a dumping ground for our emissions. And of course, when we produce trash solid or liquid, and we put the trash out on the street, we have to pay for it to being removed. But we're all emitting and adding and polluting our atmosphere for free. And in the end, what we're doing with this, we are basically taxing future generations who will have to deal with the impacts of our emissions. So I want to show you now a little bit what some of these impacts are. But before I get to that, just a quick reminder of where these emissions actually come from. There's a lot of discussion as to which country emits how much. And there's, of course, sort of a blame game that is going around in political circles when nations meet under the UN umbrella to try to rein in emissions. There's a lot of discussion of the rapidly growing emissions of China, for example. But if you look at how much we emit per person, you can see that we in the United States emit much more per person than other countries do. For example, we emit more than twice as much as a person in China or in Europe does. We emit more than 3 times as much as the average person on this planet. And the main reason for this is because we have an incredible amount of hunger for energy. And that's shown here in this figure. So the United States, that is shown here by the green bars, each bar is 1 year. So this basically shows the energy use over the last 20 years in the United States. And there's some good news here, and that is you can see that our energy use is actually coming down per person, but it's still twice as much as the energy use, for example, in Europe, and it's much, much larger than the energy use in China or of an average citizen in the world. So in my own work, I work mostly with snow and with ice. I work on glaciers in the tropics. So I want to show you a little bit what the impacts of climate change on our warming planet is related to ice, because ice lends itself really well because we can actually see the changes in our environment. And I first want to show you a few examples from Greenland. So if you fly over Greenland during the summer months and lower elevations, it now looks like this. We have large lakes that are forming on the ice, and these lakes are simply forming because the ice is melting. It forms an entire networks of river channels, and the water pools sort of in the lowest elevations on top of the ice. Here is another example. You can see a little bit more the size of some of these lakes. You can see some tents of scientists here in the foreground. Now, if the forming of these lakes was all that would happen, it wouldn't be such a big deal, because in the winter it gets cold enough, the water would freeze again and we wouldn't really lose any ice. But what we're observing is that a lot of this water is actually disappearing in cracks and crevasses, so-called moulins in the ice. And the fear is that this water is reaching bedrock. Greenland is a huge ice sheet, and it sits on top of bedrock. And it is slowly, under the force of gravity, the ice is moving towards the edges of the ice sheet, and then it is dumping ice into the ocean. And if this water is now reaching bedrock, it will lubricate the interface between the ice and the underlying bedrock. So it will speed up this process. The ice can move with less friction and faster towards the ice. It's a process that is not very well understood, but we do know that we are losing more and more ice from this ice sheet. We can measure this with satellite data, and shown here is a time series from 2002 through 2019. And what this shows is how much ice we are losing from Greenland in gigatons of ice. And again, you can see this is a wiggly line. It kind of goes up and down. And that's because in the winter, it's cold on Greenland, it is snowing, so the ice sheet is gaining mass. So this line is going up. But then in the summer, when it gets warmer, we have melt occurring and the ice sheet is dumping ice into the ocean, so the line is going down. But you can see that superimposed on this seasonal cycle, there's a clear downward trend. And I wrote down some numbers here on the left. We had 2 years in particular when we lost a lot of ice, in 2012, and then again, most recently in 2019, where in both of those summers, we lost more than 600 gigatons of ice. On average, we're losing about 260 gigatons every year. And of course, this all ends up in the ocean. It leads to sea level rise. And to raise sea level globally by about 1 millimeter, that's about the same as adding 360 gigatons of ice into the ocean. Now we're also losing ice on land in smaller glaciers. And I just want to show you a couple of examples on glaciers that I have worked on because I think they're sort of interesting case studies. One is in Bolivia. This is a glacier called Chacaltaya. This is an interesting glacier because this used to be the world's highest ski resort at almost 18,000 feet. It's about an hour's drive from the city of La Paz. You can actually see the road that is going up here. Here where you have this red star, that's where the ski resort was. You could put on your skis and ski down. This dashed line shows you the ski lift. The city of La Paz used to have an alpine skiing club. You could go up there and ski. And when I first visited in the 1990s, there was still a glacier there. You could still ski. 10 years later, this glacier had completely disappeared. And we're seeing this happening now around the world, in particularly with smaller glaciers, that they are becoming smaller and smaller and eventually completely disappearing. Here's another glacier I have worked on. This is Kilimanjaro in Tanzania in East Africa. This is the highest peak in East Africa. It became very famous, of course, with a novel of Ernest Hemingway, The Snows of Kilimanjaro. This is a picture taken from an airplane in the 1930s. About 75 years later, it looked like this. You can still see these small slope glaciers here up on the crater. Kilimanjaro is actually an extinct volcano. And I went up there with some colleagues almost 20 years ago now to install a weather station on one of these glaciers. And when you're inside Kilimanjaro, it looks like this. So we're now inside looking out. So this is actually the crater wall. And inside Kilimanjaro, you have these huge vertical cliffs of ice. They're about 50 meters tall. You can see our camp here, the tents. We camped very close to one of these ice sheets because it's a very, very dry environment. And the only water you have is the water that is dripping down from these ice sheets. So we would put our water bottles here right at the foot of the ice, and it would just drip from the ice. And a few minutes later, you would have a bottle full of crystal clear water. But then a few years later, and these are not my photos, these are photos from a National Geographic magazine, other people witnessed the collapse of one of these ice sheets. And you can see the water that is gushing out here. This collapse occurred because this ice was just drained with meltwater. It became unstable and it collapsed. And then we realized that camping right here is maybe not such a smart idea. But we didn't know that at the time, of course. So here is just a compilation of different studies from Kilimanjaro. So the actual crater you can see here. Everything that is in blue is ice. And this starts in 1912 and goes through about 100 years. The early images here, these are from maps and then from aerial photography. The more recent ones are all from satellite images. And you can see that over time we have been losing more and more ice, and the projections are that we will lose all the ice in the coming decades here on Kilimanjaro. So all this ice ends up in the ocean, and therefore we have sea level rise. And that is what we refer to as an increase in ocean mass. And that's these blue lines that you're seeing here, the upward trend in sea level. But there is a second reason why the sea level is going up, and that's shown by the red line down here. And that is that not only our land is warming up, the oceans are warming up as well. And when water warms up, it expands. And it can only expand in one direction, that is upward. So there's actually two factors that come into play here. The expansion, the thermal expansion, and the fact that the melting ice adds more and more water into the ocean. And when you add up the red and the blue aspects, you get the total sea level rise, which is shown here by the purple and the black line. So currently sea level is going up by about 3.3 millimeters globally every year. Now, sea level rise is not the same everywhere, and that may seem a little bit counterintuitive at first. There's a number of reasons for that. The fact that the warming is unequal, we have ocean currents, but also that the coastline is not stable. In some regions, coastline is actually also going up. In other regions, it's subsiding. But you can see here, this is an estimate of how much sea level has gone up along the coastlines of the US in the last 55 years. And you can see that in the Gulf of Mexico, but also along the coast of the Northeast, we've had a sea level rise of 6 to more than 8 inches over that period of time. And of course, the biggest concern with sea level rise is not so much the gradual increase in sea level rise, but is when we have strong coastal storms associated, for example, with hurricanes. Because then we now have a bigger storm surge superimposed on the sea level that is now higher than it used to be in the past. And I'm not arguing that these coastal storms per se, such as Hurricane Harvey, as you see here, were caused by climate change. But they now form an environment that is quite different. We have warmer ocean temperatures that make these storms more intense. We have warmer air temperatures. That means that the air can hold more water vapor, also making the storms more intense, the rainfall more intense. And very important also, we have completely transformed our coastlines. We now have big cities, large infrastructure, parking lots. We have sealed the surface, making it much harder for the water to infiltrate and therefore making coastal flooding much more likely. So this is one example of extreme events, and we here have an expert in extreme events. So I'm now going to turn it over to Thomas Favata, who will talk a little bit more about what extreme events actually are.
And thank you, Mathias. And yeah, so I'm going to talk a little bit about extreme events, what they are, and why they're important to study. So according to NOAA, an extreme event is classified as an event that's in the top or bottom 10% compared to the mean climate. And this can be viewed in terms of either magnitude or frequency. So we can do this with precipitation. So think about it as magnitude would be one very large storm that dumps a lot of precipitation, where frequency could be over a long period of time, you have just an accumulation of rainfall that is anomalous, meaning more than the average mean climate. So this is a curve representing climate that you could experience within a region. So the yellow curve you see is the current climate, you could say. So there would be the 10% on the bottom, the minimum. So you'd have, we're looking in terms of temperature here. So that would be your cold extreme weather. And then on the top, you'd have your 10%, your more hotter weather. So in a climate change scenario, you would have an increase in the average temperature. So this curve would shift. So that's now the red bell curve. So in a hotter climate, based off the previous thresholds, you would have more record hot weather, which is shown in that top red region, and you would then have less cold weather, but there would still be extremes on both sides of the bell curve. So you still could have extreme cold weather. It would just be not as prevalent as the more extreme hot weather in this scenario. So why should we care? And there's a bunch of different effects that either affect everyday life or the economy or even the environment. And I just listed a couple here. So you have flooding that could destroy houses. decreased water supply, especially in areas in like Southern California that really need the water. So if you get a big drought, they won't be able to have it. Health complications with heat stroke. So as it gets hotter in areas where they're not used to it, people could have more occurrences of that. And then for agriculture, as I was looking through, I don't know a lot on the subject, but I even saw stuff with like pollinated animals. So when you're losing different vegetation like trees and flowers, there's less pollinated plants. So those animals or bees or insects would then decrease for the subsequent years. So even more future decreases in plants would occur. But that also occurs in agriculture as well with drought. And then you need more water to support your farms as well. And then that the same thing with the other end of the spectrum with floods, where they could ruin the fields and destroy infrastructure. And then environmental droughts promote forest fires. So if you have extreme heat and drought, you have a higher chance of forest fires. And then again, I got into a little bit with the pollination, but you can alter biomes and animal structure just from a prolonged extreme event. So now I'll talk about the different ends of the spectrum with temperature. Okay, yep. So heat wave, just abnormally hot conditions compared to the mean temperature of the region. So this is the top 10%. And then as it showed in the curve, the mean temperature, as that increases, those extreme events will become more extreme. So a little bit more into the health problems that I stated earlier. So the heat stress is big, but there's also psychological effects that I saw in some papers where it could increase anxiety, depression, and overall production in people. So that's a negative effect that could happen to all of us. And then infrastructure, so roads could crack. And a big one I saw was power. So we only have a certain amount of power, and in these extreme events, it stresses our power plants and could actually cause sometimes just shutdowns and blackouts. And then all the stuff I got to earlier with vegetation and agriculture as well. So one of these heat waves was the North American heat wave of 2006. And this plot is in anomalies. So as Mathias pointed out earlier, this is just based off of the mean climate in the region. So you can see in the Midwest, there's very large temperature anomalies. In some places, 10 degrees Celsius higher than normal, which is massive because this isn't even Fahrenheit, this is Celsius. So there was at least 225 deaths over the course of July 15th to August 27th, which this heat wave lasted for a long time and actually went across the country. So we see here one snippet time period, July 12th to the 19th, but it did work its way from the west to the east coast over that whole time period. And there were tons of blackouts and destroyed roads and infrastructure that accompanied this heat wave as well. So the other extreme is cold. So abnormally cold conditions compared to the mean temperature of the region, that bottom 10%. And again, it will decrease due to the mean temperature rise due to climate change, but it will still occur. And one of those ways it could occur is due to volcanic activity, which could either amplify or even create the conditions due to the blocking out of the sun, and that would promote these colder conditions. So this will, to a lesser extent, destroy like infrastructure. So you'd have like freezing pipes and cause more accidents, but you do have also the environmental and agriculture impacts, especially in the tropics with fruit production. And as you can tell, I'm spending a lot of time on food because I like food. So I think that's important to look into. But so fruits and stuff, you have only are supported by a certain type of climate. So if you have these time periods where you have colder than average temperatures, that can impact a yield greatly and really affect the rest of the nation where they're importing these fruits from this region. So the North American cold wave, pretty recent. I wanted to pick a different types of case studies throughout all these, so you'll see a little bit different time periods and descriptions for all of these. But in this one, you have crazy cold temperatures. You have snow reported in urban areas of Hollywood. And even Michigan schools and businesses closed from January 30th to the 31st. And that was because of power. Again, the power was strained. There was too many people turning on their heat, and businesses doing that basically it blacked out certain places in Michigan, and the governor just shut all of it down. So these are very important to study, obviously, because you can see there are real life impacts to these weather events, and to understand how climate change could affect this. So now I'm going to talk a little bit about precipitation. So drought, which is the anomalous lack of precipitation, so that bottom 10% again. And this is due to prolonged high pressure conditions. That's one of the many ways that you could promote drought in a region. And again, to some of the effects, you have forest fires, drying of wetlands, and decline of health, which I'll get a little bit into in the case study for this. But also this goes hand in hand with heat waves, as high pressure will most likely cause drought and heat waves in a scenario. So that will do the same health effects if a heat wave is also along with it. But then you have the economic impacts, where farmers will have to increase money output, pay more money to import water if you're in Southern California, or even just lose crops because they can't access enough water. And then just your average person, I mean, conserving water, governments may ask you to not use as much water as possible if you're in a strong drought. So that's another impact. So the Dust Bowl. So this is a more historic drought, but you have two main things that went into this. So you did have a lack of rainfall over the Midwestern US, which was a big reason, but also over farming. So you have area of farmland that was just dirt, basically, because it was all dry, and they didn't have the same technology as we have now to irrigate and put water in those areas. So they just turned to dust and lost a lot of farmland, and these giant dust storms went across the country. And health effects with dust, you don't really want to breathe them in. So there was a lot of people having problems breathing, and all other adverse health effects, and again, destroyed crop yield. So drought is very important to sustaining agriculture across the United States. So then the other end of the spectrum, extreme precipitation. And this is attributed to low pressure conditions. And due to climate change, there'll be more water vapor in the air with the increasing temperature. So there will be, in a sense, more extreme precipitation you would expect. So that would be increasing floods, increasing landslides in the regions where those would accompany like extreme rainfall, or you would have hilly regions with landslides. And then economy, you can look at like the more magnitude storms. So you'd have like heavy storms where you could have like with hurricanes, you would have increased storm surge or increased winds that could destroy buildings. And then again, loss of agriculture, which really fuels food across the United States. So this one, it wasn't that big, but I saw this this image, which I really wanted to talk about. So I attributed that figure to this slide. But this was a floods in Louisiana in 2016. So multiple feet of rain fell over the course of a couple of days. It was only over a short period of time, August 9th to 13th. But it was classified as a 1 in 500 year event, which just means that this strength of event would only happen 1 in 500 years. Around 40,000 homes were estimated to be destroyed. So how exactly would we classify climate change to any of these extreme events? Well, why isn't it just chance? Well, it kind of is chance. You can look at it as statistics. So you can think of it as a bet. So what are the odds that this event could happen? And climate change increases the odds that these events would happen. So you'd have the risk of these similar events in this case, or under these scenarios, would be increasing 40%. And the amount of rain for these types of events, the intensity, the average would be increasing 10%. So you are more likely to have these extreme events under these conditions than before without climate change. And this again goes to that curve I showed you with the increasing mean shifting where the extremes are. I just wanted to show a different way to explain that same plot. And then just a little bit on El Nino and La Nina. I'm not going to go too much in depth. I just wanted to show that how this changes the mean as well. So El Nino and La Nina are sea surface temperature oscillations over 2 to 7 years. And basically it's just warm water. El Nino is warm water in the eastern tropical Pacific. And then that water moves to the west for La Nina, and then there's colder water in the eastern tropical Pacific. And this affects the atmosphere, which in turn affects the climate, well, infects the climate and weather over land. So in the images to the left, this shows El Nino impacts seasonally. But basically, I just wanted to point out that some regions get drier or warmer or wetter or cooler, and this will then shift that mean climate. So during an El Nino year, you could have warmer weather in the Northeast in America where it shows there. So this would shift your climate curve to the right, and you could have more intense extreme heat events in that area. And this would be the same for all the areas you see where it's wetter or cooler or drier. So I just wanted to point this out, that it's not just straight climate change, like increasing linearly, that there are other processes that also accompany this that could affect and increase or decrease the number of extreme events within a given region. And now I'll pass it back to Mathias.
Great, thank you, Tommy. So the last 5 minutes, I thought we would spend to talk a little bit about what some of the options are moving forward, because we don't want to leave you with the message of all these climate change problems. And I want to stress that there's a lot we can do in the many different avenues where we can move forward. And there's this famous quote by John Holdren, who used to work in the White House Office of Science and Technology Policy under the Obama administration, who basically argued that we had these 3 choices: mitigation, adaptation, or suffering. And of course, nobody wants to suffer, so we have to invest in the other 2. Adaptation, meaning trying to adapt best as we can to impacts that we know are coming or already here, and then trying to mitigate climate change. So how do we do that? There is not one silver bullet. There's not one thing we can do to basically stop climate change, so to speak. But we can move forward in many different avenues. And I just want to show you a little bit what some of these options are that we have on the table. One thing that I think is fundamentally important, and that's why I showed you this video before, is that we cannot continue to pollute our atmosphere without paying for it. We have to, in one way or another, find solutions to put a price on carbon. And in fact, this is happening increasingly around the globe. This figure here shows you different regions, countries that are already trying to put a price on carbon. This can take the form of a cap and trade system, where you are given a certain set of allowances to emit. And if you are under that limit, then you can basically sell your allowance to another industry that has a harder time and then has to pay for it. And you gradually lower the allowances over time. It can be that you set a straightforward tax on emissions, or it can be that you do something in the sense of carbon offsetting, where you, if you have to emit CO2, you have to at the same time invest in another activity that reduces emissions by the same amount. You can see that we have some activities like that already in the US. For example, we have a cap and trade system in the Northeast known as the Regional Greenhouse Gas Initiative. We have an international cap and trade system between California and the province of Quebec in Canada, for example. That is more on the policy side. Other scientists argue that we need to do more on the technology side. So why do we have to emit carbon dioxide in the first place? Couldn't we possibly just capture the carbon right at the source, compress it, reduce its volume, and inject it underground? For example, this is now increasingly being debated that we could do this by retrofitting coal-fired power plants, for example. There are also increasingly efforts to try to actually suck carbon out of the air, as you see here in this picture. That's still very difficult to do at this point. There are technological issues because the concentration is very dilute. It costs money and it requires energy. But we have to invest in these technologies, advance the science to see whether this could also be a possibility moving forward. And then we fundamentally have to change the way we produce energy. Right now, we're still doing this by burning coal, oil, and natural gas. And we have to go away from that and start to invest more in renewable energies. And again, if we look across the Atlantic, what the Europeans are doing, they're way ahead of us, for example, in terms of wind energy. We have big wind farms in the United States, but they're all on land. And the big potential for wind energy is not on land, it is offshore. Countries such as Germany, Denmark, the UK, Sweden, Norway, they have transformed the North Sea into one giant wind farm. And some of these countries today already receive half of their electricity from wind alone. We are moving in that direction now in the US too. This is one of the few wind farms we now have off Rhode Island, Block Island, but it's very, very small. But we're now moving forward with this in New York State, also in Massachusetts. So that's a very good move forward. I don't know if you've ever been on the shore and just looked at the waves coming in, and you ever thought about the tremendous amount of energy that we could harvest from tides, from waves. Again, this is a technology that is still in its infancy, but if we could scale that up, it could also provide enormous amounts of energy for us going forward. And then, of course, there's solar energy that we can use in many different forms for electricity, for heat, for biofuel. You can scale it from a small solar panel on your roof to giant solar farms, as you can see in this picture. We can use the energy from underground, geothermal heat. Again, this is also scalable from just heating one house to big power stations, as you can see here in this case, one example from Iceland. So here's sort of the summary slide where we are right now. You can see that right now, all these renewables, while they're trending upwards, we're not producing enough energy on a global scale, still from renewables. We're still right now burning fossil fuels, and we have to work on this in the coming decades to get off this fossil fuel train and start producing energy in large quantities using renewables. And finally, the last thing that I think is really, really important is to realize that climate change is a global problem. It's not the problem that one country caused alone. It's also not one problem that one country can solve alone. We can think of this as a puzzle, and every country holds a piece to the puzzle, and we have to cooperate and work together. And you can see here in this cartoon that, you know, different countries are approaching this problem in different ways. Some are actually asking scientists for help, which I think is great. Some are arguing with one another, but some countries, unfortunately, also are obstructionists right now. And you know that the United States, for example, has pulled out of the Paris Agreement. And I think it's fundamentally important that we do not leave this international negotiating table, that we contribute our part going forward, because it will affect not only us, but it will affect future generations. Okay, so I think I will end it with this. Thank you so much for your attention. You can visit us on our website, on Instagram. Great. All right.
Okay.
Thank you all for joining us.
Thank you, Mathias. Thank you,
Thank you,
Tony.
guys.